Okay, I forgot to sign in sheet, so I'm going to pass around a sheet of paper. The back of it is something we'll be going over next week, so don't even worry about it. Just please print your name because I can figure it out later. Labs, all black here. Okay. We'll go ahead and get started then. So don't forget out with our reminder tomorrow. That's why there was no puzzles for tonight. Number 2, you do have a homework due on Sunday at 11:59 p.m. I apologize for the delay in getting it posted. I did post it this morning. If you have not done the math connect puzzles associated with the degraded rate laws, they are due also this Sunday at 11:59 p.m. And then finally next Monday is exam number 2. Look at Blackboard to see what will be on the exam. I believe the only thing that's listed there that is coming off is I am not going to put reaction mechanisms on the exam. Now, as far as what you will receive when you get your exam on those back pages, like you had last time, that you removed from the exam, you will have your periodic table again. You will have a formula and constant sheet, and you will have your solubility rules. Now, formula and constant sheet, folks, I don't make it just straightforward. In other words, I don't put everything with the 0th integrated rate law together. Everything with first integrated rate law together. You got to know what you're doing. You got to know what you're looking at. I don't make you memorize every little detail, but you should be able to recognize what you're working with and when to work with what. So keep that in mind as you're progressing. Any questions? But you will have all the formulas will be on there somewhere. We've done a lot of formulas this week. The only formula I refuse to put on this test, so don't even ask, is molarity and density. If you don't know those, you don't need to be in Chem 2. You need to go back to Chem 1. But the formula for molality will be on there. The formula for mole fraction will be on there. The formula for the change in temperature for boiling point will be on there. It will all be there somewhere. But you gotta know what to do. Questions? Yes. Did I only give it one? I'll go back and give it a second attempt.
Also, one of them on there, I think is incorrect, because it doesn't allow you the option.
You'll have to send me an email about that one, because I don't know what that one is, so. But I will go back in, no, homeworks always give 2 attempts, so I don't know why I hit the 1 attempt. I'll go back in and give it an attempt. Only on quizzes am I that tough. Or tougher. Other questions? This is what I'm getting at, folks. I'm not gonna get mad if you bring up stuff. And if that problem is truly incorrect, it will come off the actual problem sheet because, and I'll report it to active so that it can get corrected. But I gotta know these things so that I can do my due diligence. Okay. So what we're doing today, I'm going to start with a bunch of pictures, to be honest, because that's the easiest way to explain some of this stuff. But we're going to focus on collision theory, energy of activation diagrams, including how a catalyst alters the energy of activation. And then we're going to be working with the Arrhenius equation. The Arrhenius equation allows us to calculate the energy of activation if we know the rate constants and the temperature, or it allows us to calculate a rate constant if we know everything else. So we're going to be using the Arrhenius equation, and folks, you've actually already seen something very much like the Arrhenius equation that we will be using primarily because it's very much like the Clausius-Clapeyron equation. So that should help a little bit in, because you already have mathematical skills from the Clausius-Clapeyron. So that is the plan for today. If I have time, I will start getting into reaction mechanisms. But I don't know if I'm going to have time, and that's why they are not going to be on Monday's exam. And even if I did have time to get started, I would not have time to do it properly. So, okay. So let's go into there. Okay, let's see if it'll. So collision theory. We've already actually introduced this concept, but I don't know if I've termed it collision theory. Collision theory basically says that the molecules must collide with the correct orientation for a reaction to occur. So in this particular example, you will see that we have a hydrogen going into the going into a double bond area. Looks like, even though you can't really see it. And that would be a good collision. But if you turn that molecule around, you're not going to get a reaction because that collision is not going in the correct direction. Same thing here. If you have the green molecule and it collides with one of the black atoms, if it's not coming in right at that double bond, it's not going to have a proper collision. So again, this is basically illustrating that the molecules must collide with the correct orientation for a reaction to occur. You get anything else, any other orientation, the reaction is not going to occur. Now, what can we do to get these molecules to hopefully collide frequently with correct orientation? Huh? Well, we can't hold them still.
Again, the correct orientation.
It would be very difficult to do that unless you're putting it on something.
No.
Catalyst can help. But what else can help?
More collision.
More collisions. What's going to cause more collisions? Heat's one way. Higher concentration. So let's face it, if I only have a couple of molecules, they may or may not collide with the correct orientation. But if you put a ton of those in there, there's a pretty good chance that they're going to collide with the correct orientation. You're going to get some collisions with correct orientation. Now, besides the orientation, you also have to have collisions with the correct energy. And what this is showing, even though it's not important, this is my framing, is you have two different molecules. You have an orange molecule and you have a green molecule. And this molecule, in this green molecule can come together and bounce, and then they're separate. Kind of like what was discussed with an ideal gas. They collide and then they go in the opposite direction. So if they don't have synergy, they're just going to collide and they're going to bounce off of each other. They have to come in with the correct energy. And only if they come in with the correct energy, you can get green and orange molecule. Only if they come in with correct energy do you have the ability for those to collide and form something. Now, we've already discussed concentration helps, but what else did we say? Temperature. And temperature is the biggest factor here because temperature provides energy. Heating a mixture up provides its energy. And if you provide it with more and more energy, then yeah, they're going to collide and they're going to have a lot more energy when they collide so that a reaction is more likely to occur. Now the question is, how much energy is needed for these reactions to occur? And that's where an energy of activation diagram comes into play. And I'm actually going to draw it instead of using this, simply because I want to get rid of that screen. So when you have an energy of activation diagram, from a general perspective, on the x-axis, we are talking about the reaction progress. On the y-axis, you are talking about energy. Now, if we're talking about a reaction, when we look at a reaction, the reactants are on the left. So that is our starting point. Now those reactants, we just said those reactants have to collide with the correct energy. That correct energy is dependent upon the energy of activation. If it has the correct energy to get over that barrier, then yes, we have the ability to go and form our products. Now I'm going to describe this difference between the reactants and the products in terms right now, because it's the only term we've ever really talked about in college chemistry. We're going to describe it in terms of the enthalpy, the heat of the reaction. Now you can, as we will discuss when we get to like chapter 17 to 18, we tend to discuss it in terms of Gibbs free energy, which would be accurate, actually more accurate. But as you'll find out when we get to that chapter, when we talk about Gibbs free energy, it's mostly enthalpy anyhow. Okay. Now, in this particular case, more energy is given off than was absorbed. So in this particular diagram, we are talking about a negative delta H because more energy was lost by the reaction than absorbed. And in other words, this is an example of an exothermic reaction. But not all reactions are exothermic. We also know that we can have an endothermic reaction. Even with an endothermic reaction, your reactants will be on the left. You will have an energy of activation that must be overcome in order to get to the products. That energy of activation is the distance from the reactants to the, in this particular case, if I'm going this direction in a reaction, it is the distance between the reactants and the top of the curve. And the difference between the reactants and the products is going to be related to its enthalpy. Now, in this particular case, you had to put in more energy than you got out. Because you put in more energy than you got out, this is a positive enthalpy. And so this is an endothermic process. Now, folks, just because I have been doing the reaction in a forward direction, we'll be getting into reactions that are reach a state of equilibrium. And you can have a forward process and a reverse process. You need to pay attention to the words. Because let's say I have energy. I draw, we'll go with the same one I just drew. If I say, okay, what is the energy of activation for the reverse reaction? Well, the reverse means you're starting with your products. So this would be its energy of activation. In other words, you got to pay attention. Are we going forward or are we going in the reverse? Now, I will reiterate something that was said in College Chemistry 1. As a reminder, exothermic reactions tend to be spontaneous. In other words, once they get that spark, they go. Whereas endothermic reactions are not spontaneous. Now, folks, just because we are using this word spontaneous doesn't mean it's easy. Just because we say it's going to go doesn't mean it's going to do it, so it's going to be easy. Because if we go back to my first diagram, this is a exothermic reaction, but from an energy of activation diagram standpoint, this is easy. Because it has a very long energy of activation in order for the reaction to occur. Now it's easier than it would be to go in the reverse direction, because if it were going in the reverse direction, it would have a nasty energy of activation to deal with. But it's still, I mean, this, even though it's exothermic, it doesn't mean it's easy because it has to overcome that energy of activation. That's where a catalyst can come in. What is a catalyst, anybody? Okay, so it's a substance that lowers the energy of activation. Is there anything else we can say about a catalyst?
They're not used up in the reaction.
It's not used up in the reaction. So a catalyst enters and exits the overall reaction. Yes, I'm using this word overall on purpose. The same. It enters and exits the overall reaction and appears exactly the same. It's unchanged. Now, we can get a catalyst to do this in a variety of different ways. One, let's just take our example that I had just a moment ago, which was an exothermic process with a decent sized energy of activation as we went from reactants to products. Basically, what a catalyst would do is it would find an alternative path. That alternative path simply is going to have a lower energy of activation. Now, in this particular case, this is a one-step alternative path. Because we only have one energy of activation pump, if you will. But folks, you got to remember, all a catalyst is something that finds an alternative path. It doesn't have to say that that path occurs in one step. Now I will pull my pictures back out. Here's an example. I know it's not ideal. But you have your reactants, you have your products. This is your original energy of activation, which you can't even see the top of. In this particular case, what they did is they added a catalyst to go from the reactants to the products. But it kind of took that energy of activation and it distributed it over a multi-step process. This would be considered a two-step process. And of those two steps, the first one has the higher energy of activation. Because once you get to the second step, you have a very low energy of activation. So it lowered this thing down some. But in doing so, it had to do so where it made it over a two-path method, a two-step method instead of just one step. Questions? Now, these points along the way do have names. The top is going to be considered to be a transition. Literally, the molecule is in a transition phase as it is undergoing the reaction. And the bottom between those 2 points is called an intermediate. So you have transitions at the top and intermediate in the trough. We will be discussing those in a lot more detail when we get to reaction mechanisms too. Because this is directly related to this example here on the left, on the bottom, is going to have more than one reaction that makes up the overall reaction.
Top and bottom again, sorry.
The one on the bottom will have more than one reaction that makes up the overall reaction.
Oh, I did, sorry, I was thinking.
Oh.
The
two,
wrong.
the trough is the intermediate.
Okay, and the top is three.
And the top are the transition states. Huh? Both of the tops would be a transition because if you can almost think of this intermediate. Let me see. Let me do something. I don't think I can do that. There it is. I just have to figure out what one. You can almost, basically the reason is you can almost think of these points. The reason they're called transitions is you can almost think of this as a product that is temporary. That's why it's called an intermediate. Because you go from your reactants, you go through the transition and you hit the first product. Then that product made from that first reaction then reacts to get another transition before you get to your actual products of the reaction. Because the reaction itself is just the reactants and the ultimate products. Question. So the overall reaction is where you started and where you ended. But you got a temporary, and it is temporary, intermediate that acts like a product of a first reaction that then is used in the second reaction. We'll talk about that more. Okay. So now only one thing I wanted to describe, because I think it's on our homework, and it's a very important catalyst. that almost everybody, if not everybody's heard of. Enzymes. Enzymes are these monster protein chains that have wrapped around and done their thing, and they have this active site. And what happens is you have your substrate, the molecule you want to undergo the reaction, it enters into that active site, and that active site starts pulling that molecule apart so that the reaction can occur. And then once the products are made, this picture in the active site, the products are going to be shot out of it, and you're left with the enzyme inside. So an enzyme is just our biological catalyst. It all depends upon what reaction we want, what this composition has to be. Okay, so let's get to the math. So we've been talking about this energy of activation and stuff. We've been talking about rates of reaction. Rates of reaction, energy of activation, how do they go together? Because you got to get over that hump for the reaction to occur, you know? So let's talk about our energy of activation. Now, the original equation, that is the Arrhenius equation, is that the rate constant is that the rate constant is equal to a frequency factor times the exponential of negative E sub A over RT, where E sub A is our energy of activation. R is the ideal gas constant of 8.314 joules per mole Kelvin. And T is the temperature in Kelvin. Now, when you take the natural log of everything, you get the equation of natural log of the rate constant is equal to a negative E sub A over R times 1 over T plus the natural log of the frequency factor. It's this. Now, if you have a graph, you can use that graph.
because you have y equals mx plus b. So the slope of your line is equal to a negative e sub a over r. Meaning you have a way to determine the energy of activation by graphing the natural log of the rate constant versus 1 over t. Now we can expand this equation that I gave you further, and we get to the equation we're actually going to be using, which the natural log of K2 over K1 is equal to negative e. Oh, yeah, it is. Negative e sub a over r times 1 over T2 minus 1 over T1. Which, folks, this should look very similar. This is our Arrhenius equation, which should remind you of the Clausius-Clapeyron equation, which was the natural log of P2 over P1 was equal to negative delta H over R times 1 over T2 minus 1 over T1. They're quite similar. So you should have the skills to perform this math. So let's do a problem. Calculate the energy of activation for a reaction that by changing the temperature of the reaction from 273 Kelvin to 300 Kelvin, causes the rate constant to increase by a factor of 7. Okay, so basically what we have here is we have a T1 of 273 Kelvin and a T2 of 300 Kelvin. And we know that it changed its rate constant by an order of 7. Doesn't matter what I put in there, it's an order of 7. And we were asked to determine the E sub A. And we know that R is 8.314 joules per mole Kelvin. So our natural log of K2 over K1 is going to equal a negative E sub A over 8.314 joules per mole Kelvin times 1 over T2, 300 Kelvin, minus 1 over T1 of 273 Kelvin. So we get 1.946 is equal to a negative E sub A over 8.314 joules per mole Kelvin times negative 3.297. In other words, all I did was kind of start simplifying things. Negative E sub A over 8.314 joules per mole Kelvin is going to be equal to a negative 0.590. So E sub A and the Kelvin actually has already canceled out. The E sub A is equal to 4.91, and that would be in joules per mole. Double checking on the map. Oh, I'm glad I did.
Okay.
What's going on?
Negative 3 over 9100, and I'm like, where did you get 3.92 or 9?
That's why I always, it's hard to type and talk and write. So it's easier for me if I do it and then I go back and check it. So I always check my math because I know I'm horrible at these things. Let's go with 49,000. 100 joules, or in other words, E sub A could be equal to 49.1 kilojoules. And I did the same mistake of other students. I've seen a lot of students here. I forgot my time skin. Because it was there. Any questions? Let's look at another. Well, it's about time for our break. So instead of starting the question, we're taking a break and then we're going to come back and do more questions. So you get a break for about 4 or 5 minutes today.
That's
Yes.
sitting here like.
That will work.
But I am just. The rock and box.
I can email them and. Too much on what I had planned. Ask me.
That's fine. I think.
Yeah, I don't know. That's the only problem. I don't know.
That is fine. I'll email.
Because I have to ask you and see if I can, it shouldn't be a problem because I only make 2 guys sign up, so I can start posting that one.
Well, I'll email you remind, or to remind you. Thank you.
Yeah.
This stuff.
I'll let you know. Yeah. Hey.
Hey, Tao.
Come on, with one right in here.
Yeah.
Question. So today was graph, and the slope of the line is today is 1.9398 times 64 Kelvin. What is the rate constant at 30 degrees Celsius? If the rate constant at 20 degrees Celsius is 1.49 times 10 to the minus 3. And the units there. Is per molar second. Want to give you a few minutes to work on it, and then I'll come in and. I will. It would make that big of a difference.
This is. Yeah.
I'm trying to get through that math in my head.
This number is gonna go. No, this is using the same plate for the test year. Yes. So then. All right.
No.
Yeah. No, this is I agree with yeah, I guess. That's it. Yeah.
Yes, yeah.
Oh, I messed that up. Wow.
Yeah.
I was working with math real quick, sorry. Well, I can think it through.
The final answer real quick, how many debate?
This scope of the law is a negative 1.939 times 4 Kelvin. What is the rate constant at 30 degrees Celsius? If hold on, there's an error. See, even I can see errors, but I'm doing it through math.
Oh, okay. So it's still spicy. Yeah.
That's what I got, and I was like, I put a negative Russian. Okay, so again, it helped me to talk through it. Folks, I double take my math when I'm doing it, and it's hard to do when I do it in here and I'm not paying attention. So basically, I knew that I was going to be dealing with rate constant at 30, rate constant at 40. That told me I needed this previous equation. So natural log, I chose, it wouldn't have mattered who you chose as K1 and K2, as long as you kept the appropriate pieces together.
Getting the 2.045 there.
All of this multiplied by a positive 1.93 to 898 times 10 to the 4, which is amazing.
Yeah, no, I get 0.011.
That's what I get by the end. I get 2.0 on both sides still. So we highlighted these because I started, and folks, you can bring highlights. But I highlighted these so that I kept things together. So you had the rate constant at 30, well, that was the one I wanted to figure out, because K2 I made as the rate constant I wanted, which meant T2 had to be at the 30, so that was 303. The other one was at 40, which was 313, and it would have been 1.49 times 10 to the minus 3. Where I originally made my mistake was I put a negative here instead of a positive in front of the 4. But if you do 1/303 minus 1/313 and multiply that by the positive 1.9398 times 10 to the positive 4, you get 2.045. To get rid of the natural log on the left-hand side, you take the exponential. So you get exponential of 2.045 is equal to K2 over the 1.49 times 10 to the minus 3. And then e to the negative, or e to the 2.045 is 7.69 is equal to K2 over 1.49 times 10 to the minus 3. And so I got, when I multiplied the 7.69 by the 1.49 times 10 to the minus 3, I got 0.0115 for an answer. Questions? Always check your work. Always check what you did in the calculator. Especially when you start dealing with complex problems, which is what this to me is.
So I'm a little confused here. Okay, so like I figured out what I did wrong, but I got the answer just by taking that one side, and instead of doing negative 1.9398, I did that on unit of 4, and that gave me the correct overall answer.
Yes, because times 10 you can do e. Or no, you can't do x. You're talking exponential. You did it exponentially or the other e?
I did not really. The small one. Yeah. I did the small one.
Well, you should.
Chris is putting in the small e there. It's giving me the overall answer.
I would not have expected the little e there to give you the overall answer. I'm not certain how that occurred.
I don't.
Luck. What now? It's not a possibility. But the big thing is yeah, that's why I'm asking what G, because when I do times 10, I use the second E, and it's the capital E.
Okay, because I was like,
That gives me my times 10.
okay, I was using the wrong one. That's why.
But how you got it with the exponential, I'm not sure.
I don't know.
Questions?
How do you recommend studying the math portions of the test?
I've never been good at studying for
Okay, how do I recommend studying for math? Part of it is repetition. There are some problems, I can't remember if I've got plenty up there for optional homework or not. If not, I'll post some tomorrow when I have a chance to look. But doing optional homework, and it's literally for math, for me, it's always been repetition. Is the only way to make sure that I am focusing on the math. And by me going through it, if I don't have a homework up there, I'll have to create one, which means I'll have to do the answer key too. And I'll double check my math, because obviously it's easy to get lost. But I usually do my math problems twice before I get to the final answer.
And piggyback on that, in the book, they have a lot of practice problems that you can do at the end of the chapter. And they have the answers in the back, if you don't have to go up to the friend from our.
But yeah, just literally, unfortunately, the math is hard. There is no secret. Hold on, I can't hear.
problems you're talking about, would that be in front of them or?
No, there's the optional homework. I gotta look and see if I have any of the ingredients problems. I can't remember. I've had done this. I haven't taught this in 2 years. So I gotta look and see if I've done it, got any of those in there, but it'll be. If not, I'll post it tomorrow. Any other questions? Yeah, I'm cutting out early today. See you later. And if you've got questions, later, and I'll see if I can.